Last week, we defined the Laplace transform. We sort of saw it, we used Maddox, Arthur Maddox had a nice way to tie it back to power series. But this is essentially the Laplace transform. This is the definition we were working with last week. The Laplace transform of a function of t is you integrate that function against e to the minus st dt from 0 to infinity. And what happens is the t gets integrated out. So the t is the variable of integration here. But you'll be left with this parameter s. So a transform, once again, is you're going from one type of domain into another type of domain. So we're going from time into this sort of frequency space. Yeah. And then we did some examples. Right? So hopefully you've been able to. One of the reasons I had Monday off was hopefully everyone could get caught up on things. So we did these examples and we derived a couple of basic formulas. So there is a summary sheet of Laplace transforms on Blackboard that you can download. I think, for me, the way I learned these best is I made flashcards and just would quiz myself. So we have the Laplace transform of t to the m power. The power becomes the factorial, and then it's divided by Sn plus 1. And then we derive the formula for e to the at. 1 over s minus a. Right? And so we got up to now properties. So if you think about a lot of the functions we've been working on in differential equations, it's powers of t and exponentials. And so now we're going to see how the properties of the transform itself to help us take formulas for the individual pieces parts and how we put them together. So that's one of the big ideas in math. I haven't really been mentioning it too much in this course, but there's the idea of analysis. Analysis, sort of the broad idea is when you take something complicated and resolve it into its parts. And then there's synthesis, which is when you take those parts and then put it back into something complicated. All right? That's one of the big themes in math. So we know how the Laplace transform acts on these basic parts. Now we're going to see how we can put those parts together. The Laplace transform is a definite integral, so it shouldn't be too big of a surprise that we have linearity. So how would we actually formally prove that? So once again, what linearity, the way I like to think of it, linearity preserves linear combinations. So if you have a linear combinations of two functions of t and then take the Laplace transform, that's the same as taking the same linear combination of their Laplace transforms. So you can either do the linear combination, then Laplace it, or Laplace each piece, then take the linear combination. So how would that work? And so most of these proofs go this way. You start off with the left-hand side, and then you just hit it with the definition. So by definition, the Laplace transform of anything is the integral from 0 to infinity of this thing times e to the minus st dt. Right? So that's your Laplace transform definition. And now what I can do is I can distribute. We just kind of follow our noses here. We're just going to distribute this through. I got a c1 f of t e to the minus st plus or minus a c2 g of t e to the minus st dt. And then assuming these integrals involving f of t e to the minus st, g of t e to the minus st, assuming those exist, then we can use, at this point, the linearity of the integral. So this is going to be, break it up over addition and subtraction. And then for the last piece, we can just factor out those constants. And there we got it, right? Because this is nothing more than the Laplace transform of f. So Laplace transform of little f of t, we're going to call that big F of s, plus or minus c2 Laplace transform, little g of t, there's big G of s. And that's how all of these proofs go. All right. So as we move through the last couple of weeks, there'll be some problems on the take-home where you have to derive certain properties. If you have to derive something using the definition, then we've got a couple of these examples here for you to look at. That's how you do all of these things. Okay. All right, so with that in place, let's derive formulas for the hyperbolic cosine and hyperbolic sine. I'll do one of them, and then you can just mimic the procedure to do the other one. So let's take a look at cosh. All right? So we got to remember what cosh, if you think about the Laplace transforms we only have Laplace transform formulas for natural number powers of t to the n, and exponentials. All right? So we have to remember that cosh itself is a linear combination of exponentials. Does anyone happen to remember which one it is? Yeah, there you go. Perfect. Yeah, we missed you last week, Zeron. All right, so that's e to the kt plus e to the minus kt, whoops, all over 2. And so if I want the Laplace transform of the hyperbolic cosine, I can instead take the Laplace transform of this. And I can actually see this as a, once again, if I distribute that half through, right, this is going to be a half e to the kt plus a half e to the minus kt. So now I can use linearity here. So that's a 1/2 Laplace e to the kt plus 1/2 Laplace e to the minus kt. And now I can use one of those formulas we derived last week. I know that the Laplace transform of e to the at is 1 over s minus a. And so here I've got a k and I've got a minus k. Yep, so this is going to be 1 over, or 1/2 times 1 over s minus k plus 1/2 times 1 over s plus k. And we'll go ahead and get the common denominator there. So I need a factor of 2, a factor of s minus k, and a factor of s plus k. So this first term is missing the s plus k factor, and the second term is missing an s minus k factor. So in the numerator, when the dust settles, I got a 2s over 2 times, and I'll go ahead and multiply that out. Usually we don't multiply things out, but we'll go ahead and do that. And we get our final answer here. Laplace transform of cosh kt is s over s squared minus k squared. And if we wanted to choose some s values, so this kind of gets suppressed. Before we were kind of worried about what values of s is going to make this work. We would need s to be bigger than k here to get that exponent to be negative to make it converge, but there it is. Okay. Now, this is one of these proofs or these derivations that you can go back and easily swap things out to figure out what sinh is. I could go back and do this same thing with sinh. The only difference between cos and sinh is instead of having, if I want to write sinh here, is instead of this plus, it would be a what? A minus. And then I could just follow that through, see? So that would be a minus there, a minus there, a minus there, a minus there. So here I would get s plus k minus s plus k. So don't forget to distribute the negative. So these would cancel out, and I'd be left with 2k in the numerator, which would leave me with a k. And that's how we get our formulas here. All right, so there we go. There you go. And that's exactly right. Here we go now. Boom. Exactly, Zeron. Use the fact that the cosine of kt is the cosh of IKT, and the sine of kt is 1 over I sinh of IKT to find formulas for cosine and sine. Yep. So if you remember Euler's formula, which we mentioned back when we were doing chapter 5, undetermined coefficients, I put up, that was my very first video I made in math, was Euler's formula. It's decades old now. It's still up on YouTube, and I put it up there in the blackboard for you. Yep. So with Euler's formula, you can actually go around and derive the fact that like cosine of kt is e to the IKT plus e to the minus IKT all over 2, which that's just cosh, but instead of having cosh of k, t, it's cosh of IKT. So all you got to do is replace right. So if I want the I know the Laplace of cosh of kt, we just did. That's s over s squared minus k squared. The Laplace then of cosine kt is just the Laplace of cosh IKT. So all we got to do is everywhere we see a k in this formulation, I'm just going to replace it with I times k. I squared is -1, so we get s squared minus a negative k squared, so that's s over s squared plus k squared. And similarly, you can show using Euler's formula that if you want the Laplace of sine of kt, that's the Laplace of, it's not quite sinh of IKT. There's a 1 over I that you need. So linearity, once again, we're kind of playing a little fast and loose. We've got these non-real constants, but they behave the same as real constants. And then this would be s, or excuse me, k. So that would be ik over s squared minus ik squared. So once again, just plugging that into the formula for sinh that we just had. And the i's cancel. And we get that. Okay. So there's your sines and cosines. Now, for those of you that had me in Calc 2, you might be a little upset with me because in Calc 2, one of the integrals I had you do, and it was spread out over a couple different assignments. One of the integrals I have my Calc 2 students do is this one. Because then you gotta rewrite it as an improper integral. You gotta do parts, and you gotta use squeeze theorem. It's a whole thing. I say, well, this isn't important. This is how you get the Laplace transform of the sine function. And if you're interested in what a Laplace transform is, that'd be a great project. No one ever does that project. They just, pages and pages of this work. When they get it to work out, though, they're pretty happy with it. But as you can see, we just circumvented that using complex numbers here. There you go. So once again, I would put these on flashcards and just every day. It doesn't take long to practice these formulas. Ideally, the way you learn the formulas is you practice enough problems. But I think it's helpful to make these flashcards and kind of go through them. Okay, so our next example is using these properties. Let's do some more of these Laplace transforms. So once again, we kind of have the basic formulas now, right? So just to kind of review here, the Laplace transform of t to the n, n factorial over s to the n plus 1, where n is a natural number. We got the Laplace transform of e to the at, 1 over s minus a. The Laplace transform of cosh, Laplace transform of cosine, and then Laplace transform of sinh, and then sine. Okay. So these are the basic building blocks that we have to work with. So if you want the Laplace transform of 3 times t to the 5th, I know the Laplace transform of t to the 5th. I know that 3 is a constant, so I can move that out front. 3 Laplace transform t to the 5th. Laplace transform of t to the 5th. That's your 5 factorial over s to the 5 plus 1. So your 5 factorial, that's 120 times 3, so 360 over s to the 6th. If you want the Laplace of 3 minus 4 sine 5t, once again, I can use linearity. That's the Laplace transform of 3 minus Laplace transform of 4 times the sine of 5t. If I really wanted to, I can think of 3 as being 3 times 1. So this is 3 Laplace transform of 1 minus 4 Laplace transform sine of 5t. If you really want to, you can think of 1 as t to the 0 power. So this is going to be 3 times 0 factorial over s to the 0 plus 1 minus 4 times 5 over s squared plus 5 squared. And so you get 0 factorial, remember, is 1. So 3 over s minus 20 over s squared plus 25. You see how this is working? Let's take a look at this next one. I got the Laplace transform of e to the minus 3t times cos 2t. We don't have anything right now that handles multiplication with Laplace transforms. Yeah, if we had, we'll learn what convolution is. That's like one of the last things we do, Zeron. But yeah, convolution goes over to multiplication. But yeah, if you start with convolution in the time domain, it does go to multiplication in the frequency. Yeah. There you go. Yeah. So yeah, at this point, it's like, well, what do I do then? Well, we'll just go back, because we will find something here shortly that'll give us a different way to handle this. But right now, if we just want to use linearity, we're going to have to bust this up into exponentials. So the cat's now excited about something. So the cost of something, once again, is e to that thing plus e to the opposite of that thing all over 2. So we're going to go ahead and multiply this out. So e to the minus 3t times e to the 2t. I'm just going to write this out because I just know I don't want to. So I got the same base. What do I do with the exponents? Yeah, add them up, sum them up. I'll take the 1/2 out front from linearity. This is going to be e to the minus t plus e to the minus 5t. And then use linearity again. And now I can apply the formula we derived last time. So here, the a is minus 1, and here the a is minus 5. So when you subtract those off, you're going to get some additions here. All right, so we bust the cosh into its exponentials, simplify, use linearity. Going to get 1/2 1 over s minus a minus 1 plus 1/2 1 over s minus a minus 5 so 1/2 1 over s plus 1 plus 1/2 1 over s minus, or excuse me, plus 5, right? And at this point, there's no actual reason to put the denominators together. Let's go ahead and do that anyway, though. So we need a factor of 2, a factor of s plus 1, and a factor of s plus 5. So the first term is missing that factor of s plus 5, so I'll put that up there. The second term is missing a factor of s plus 1, so I'll put that up there. So I'd get a 2s plus 6. And then I guess we could factor that out if we wanted to. And I guess I could factor the 2 out on top and get down to here. Once again, there's no actual reason you would think of to do this. I'm just doing it to try to foreshadow what happens coming up, because the big idea here is we're going to be taking a differential equation and we're going to be moving it over from the time domain to the frequency domain. And it turns out that differential equation in the time domain is going to turn into an algebraic equation. So this is kind of the big thing here. We're going to have a time domain diffie-q, actually more specifically initial value problem here in the time domain. We're going to Laplace it over here to s. We're going to get an algebra equation, and then we're going to try to come back. And so I'm just trying to show you that, this sum of exponentials eventually looks like one of these types of things. So spoiler alert, we're going to be reversing this process here in the next day or two. So reversing getting common denominators is called partial fraction decomposition. So that's what's on the horizon here. Okay. Here's another nice property. This is called the forward shift property. There's a couple different reasons you can think of it that way. If you think of starting in the time domain and moving to the frequency domain as moving stuff forward, right? When we multiply by an e to the minus or e to the at, what happens is we shift our s from s to s minus a. So it's putting it a units ahead of where it used to be. Okay. So for example, what this says, like if you're going to multiply by, e to the 2t, then what you do is you just Laplace transform the f of t, and whatever your answer is, you just adjust it. You just replace s with s minus 2. All right, now we're going to prove this in a minute, but let's just apply this to our last example while it's fresh in our mind. Let's look at this guy, e to the minus 3t cos 2t. I've got an exponential times the Laplace of something I know. Oops, not cosine, cosh. So what this says, forward shift says, what you can do is just take the Laplace of cosh of 2t. I keep saying cosine instead of cosh. And replace s with s minus, well, negative 3. All right. In other words, I can take the Laplace of cosh of 2t and replace the s with s plus 3. You see how the shift is working here? And I know the Laplace of cosh 2t. That's what? S over s squared minus 2 squared. I'm going to replace s with s plus 3. So everywhere I see an s, either literally or in my mind's eye, replace it in parentheses, replace it with s plus 3. And by golly, I get s plus 3 over s squared plus 6s plus 9 minus 4 plus 5. And by golly, that's the same thing I got before. Okay. So how would we prove the forward shift property? Well, we'd have to go back to the definition of Laplace transform. Okay, so let's say we got our function here, f of t. Then capital F of s is the integral from 0 to infinity. F of t e to the minus st dt. If I look at e to the at f of t, and I look at the Laplace of that, and that's going to be the same thing here, except instead of just having f of t, I've got an e to the at in there. So e to the at f of t, e to the minus st dt. Now if I look at f of s minus a, what would that be? Well, I go up to my f of s, and everywhere I see an s, either literally or in my mind's eye, I'm going to replace that s with the quantity s minus a. Okay. So now the question is, can I get this to look like this? Okay. And that's the thing. A lot of times, in these derivations, a lot of times, sometimes you have to do like a substitution, which later, I think the one we do tomorrow, later substitution involved. But, here you just can just kind of match it up. Like, are these things, can I get this to look like that? And the answer is yeah, because look, I got exponentials there, right? So let's take a look at this. So the Laplace transform of e to the at f of t equals the integral from 0 to infinity. I'm just going to write the exponentials next to each other because everything's multiplied. And then I'm just going to factor out a minus t. So if I factor out a minus, I'm going to get st minus at dt, and I factor out a t. And by golly, this is the Laplace transform, except instead of having an s multiplied there, I have an s minus a. Okay, so it works. So once again, as you look at the take-homes and things the next few weeks, you're going to have these little proofs to do, depending, here's another property for you to prove. They all break down into just when in doubt, write it out. Okay, when in doubt, write it out. All right, so find the following Laplace transform. So anytime you've got an exponential factor, we can use this shift theorem. So once again, here's the Laplace transform of t squared e to the 3t. I've got an exponential times the Laplace of something I know. This will be the Laplace of t squared. And I'm going to shift s to s minus whatever that coefficient there is. So the Laplace transform of t squared, that's going to be 2 factorial over s to the 2 plus 1 power. But we're going to shift s to s minus 3. 2 factorial is 2. I'll have s minus 3 quantity cubed. If I want the Laplace transform of 4 e to the minus t sine of 2t, we can factor that 4 out by linearity. Whoops. And now I can take care of this. I've got an exponential here times the Laplace of something I know. So this is going to be 4 times the Laplace transform of sine of 2t. And when I'm all done with that, I'm going to replace the s with s minus a. Well, in this case, I can think of this as a negative 1 times t. So it's s minus a negative 1, aka s plus 1. So this is going to be 4 times Laplace transform of sine of 2t is 2 over s squared plus 2 squared. But I'm going to shift the s to s plus 1. So my final answer here, the Laplace transform of 4 e to the minus t sine of 2t is 4 times 2 is 8 over s plus 1 quantity squared plus 4, which would be 8 over s squared plus 2s plus 5. Okay. So that's your forward shift property. Okay. All right, the last example we want to do, find the Laplace transform of this function. This actually is, like, what does this have to do with the forward shift? Well, it has to do with a different kind of shift that we'll be talking about later on. The Laplace transform of this piecewise function here. All right, so what this function is is this is one of these functions, and this is one of the reasons electrical engineers love Laplace transform. This is an example of a function that's off and then it turns on. So at t equals 2, this is when things happen. Up to 2, remember Laplace transform, we're integrating from 0 to infinity here. Okay. So t is always bigger than or equal to 0. So when I look at this, from 0 to 2, so starting at 0 to 2, but not including 2, we're in the 0 state. Right? And then it's as if someone flips a switch. And suddenly, when t equals 2, we're now following the curve e to the minus t. Now this is exaggerated because e to the minus 2 is a very small number, but boom. So this is up at e to the minus 2 there. So it goes from an off state, a 0 state, to an on state. All right, so what's happening here is we're multiplying by a step function called the unit step function, or the Heaviside function, which we'll be talking about later. But these types of things are important. Yeah, exactly, Zoran. Yep, exactly. So we're going from an off state to an on state. So these types of things happen. How do you handle these with Laplace transform? Well, at this particular point, before we introduce the unit step, which we'll do here later on, what I like about this book is they kind of they ease you into all these things. It's like, here's Laplace transform, here's some examples. Here's how you do diffie-q's with it. And then they put in stuff, okay, well, here's this thing called the unit step. And here's how you Laplace it, and here's some diffie-q's with it. Here's convolution. Here's what it is. Here's some examples. Here's some diffie-q's with it. So they kind of build you up. But the way you would find this is by the definition. So anytime you see using the definition, that means you got to go back and pull out the integral here. So the Laplace transform of anything is the integral from 0 to infinity of that thing, e to the minus st dt. Now, if you look at how this is set up, for the first 2 seconds, say, think of t as time in seconds. For the first 2 seconds, the function is 0. All right? So we can use the additive interval property. So we can use the additive interval property to say, look, well, this is going to be the integral from 0 to 2, f of t e to the minus st dt, plus the integral from 2 to infinity, f of t e to the minus st dt. All right, so that's the additive interval property. And for the first 2 seconds of its life, there's nothing. So this is 0. So that's going to just 0 out. And then for t bigger than or equal to 2, it's e to the minus t. So I can put an e to the minus t in here. All right, so we can just go back here. Now I'm integrating from 2 to infinity, e to the minus t, e to the minus st dt. We've got the same base for the exponential, so we can combine those exponents. And once again, we can factor out the minus t there. What would be left up here in the exponent if I factor out a minus t? Yep, a 1 plus s. I'll just write it as an s plus 1. That's my prejudice there, is to put that in there, dt. And now we'll just do an improper evaluation of the improper integral. So once again, you're integrating this with respect to t. This whole thing here is a constant. So the antiderivative of this exponential is going to be 1 over that constant. Times that thing. Evaluated from not 0, but t equals 2. And then as t goes off to infinity. So we have a decaying exponential. So as t goes to infinity here, got my e to the minus s plus 1 t over minus s plus 1. In order to guarantee this actually goes somewhere and doesn't blow up, we would have to assume that this is actually negative. So I need minus s plus 1 to be less than 0. So I would need s to be bigger than negative 1 for that to work. So then that's going to go to 0. So I would get 0 minus this. I plug 2 in there. So when the dust settles, I get, well, whatever this is, I get a positive there. I get an e to the, I don't know, minus 2s plus 2 over s plus 1. That's my answer. Okay. Yes, thank you. Yep. Which, yeah, I'll leave it at that. Okay. So we'll see these kinds of things. But this, do you see how this is a different kind of shift? So we'll talk more about that later. That's why that's in there. All right, and there's your homework there. Things to do. And I've got an additional homework. Let me just fire up. I want to show you the blackboard anyway. We got a couple minutes. That's Calc 2. So under course content, Chapter 8. So here's this Laplace transform summary sheet I talked about. This has all the stuff we're going to be doing eventually, right? So it's up to you if you want to download it now and have it handy. It might freak you out, but this is like what we're building towards, right? That's like a summary of all the stuff we're going to learn. Tabular integration, that's a little review there. We did some tabular when we were doing stuff by the definition last time. And then here's this extra practice. So a lot of people use this resource. Here's some extra practice with Laplace transforms. You know, you can't really practice these enough to be. You want to be good with them. You want to have a good working things with that. Because what we're doing next is now we're going backwards. So it's like here's Laplace transform. You start with a t function, go to an s function. Now we're going to be working our way backwards. All right. So as I mentioned today in class, combining and getting common denominators, that's simplifying fractions. If you want to break fractions apart, that's partial fraction decomposition. Here's a link to the Heaviside method, which is it's kind of like tabular integration in that it's an abbreviated version of things. This is just a way to get partial fraction decompositions in certain cases, might help speed things up. And then, of course, there's another extra practice. So tomorrow we're going to be working on our inverse Laplace, and that'll probably take us through the end of the week. Okay? So thanks for tuning in, everyone. We got some severe weather coming today, so be careful if you're out and about, and I hope to see you back here tomorrow. Thanks again, folks.